So when I was solving this practice problem on the math subject GRE practice test, I ended up using process of elimination to figure out that the sum of the 4 primitive 10th roots of unity is exactly 1. But I kind of cheated. I didn't really show that they're equal to 1. I just showed that they couldn't be -1 or 0. And since the product of these roots was 1, I knew E must be my answer. But it bothered me a little bit to use process of elimination for something that apparently works out so nicely. So in this video, I want to prove that the sum of the 4 primitive 10th roots of unity is exactly 1. And it'll turn out that to do so, I'll be able to figure out what the sine and the cosine of 36 degrees, aka pi over 5, is equal to. There's lots of different ways you can do this, but I found 2 different ways that I thought were pretty interesting. One that's completely algebraic based, and then one that's completely geometric based. So I'm going to do both. But in this video, I'm just going to do the algebraic way. The algebraic way to do this is to give this point, the terminal point on our unit circle, 1/10 of the way around the unit circle, a name. Maybe I'll call it z. Z is a complex number, and when I raise that complex number to the 10th power, I get exactly 1. You can visualize that by just kind of adding this angle to itself 10 times. 10 36s gets me 360 degrees, which takes me over here on my unit circle. That same trick allows me to think about z to the 5th power. If I added this angle to itself 5 times, it would take me over here to this point with the real part of -1 and an imaginary part of 0. In other words, -1. Is z to the 5th power must be equal to -1. Therefore, z to the 5th power plus 1 must be equal to 0. I've got this 5th degree polynomial that I want to solve. Well, the way I'm going to solve it is I'm going to note that -1 is certainly a root of this polynomial, right? I've changed all the z's to -1. -1 to the 5th power is -1, and -1 plus 1 equals 0. If -1 is a root, z plus 1 must be a factor. So there must be some 4th degree polynomial that I can multiply z plus 1 by to get 0 as my answer. There is, and there's lots of ways to figure it out, maybe polynomial long division or synthetic division or something. But for me, it's easier to just talk myself into it. In order to get this z to the 5th power, I must have a z to the 4th power here. But if I have a z to the 4th power here, and I multiply it by z plus 1, I don't just get the z to the 5th, I also get a z to the 4th. But I don't want a z to the 4th up here, so I better put a minus z cubed here. Why minus z cubed? Because negative z cubed times z plus 1 gives me negative z to the 4th. The problem is the negative z cubed times the 1 gives me a negative z cubed, which I don't want up here. So I better add in a z squared. Here's my z cubed. Unfortunately, I get a z squared. I don't want that z squared, so I'll subtract z. This gets rid of my z squared, but it creates a negative z, which I don't want, so I'll add 1. There's this z that I don't want. It also creates a 1, but that's good because I do have a 1 up here. The product of these 2 polynomials is 0. That tells me that either z plus 1 is equal to 0, or z to the 4th minus z cubed plus z squared minus z plus 1 equals 0. I can tell the solution over here is just when z equals -1. Oh yeah, if I took this point and raised it to the 5th power, I'd definitely get -1. But that's not the solution I'm looking for. The solution I'm looking for is over here. So the solution I'm looking for must be a solution to this polynomial. A minute ago, I had a 5th degree polynomial. Now I only have a 4th degree polynomial. I guess things are getting better. What I'm going to do now is some pretty clever algebra. I did not think this up myself. I'm going to recognize that if I square this number, I do not get 0, right? If I square this number, I get this number. So because this number squared is not equal to 0, I can divide both sides of this equation by z squared. If I divide both sides by z squared, I get z squared minus z plus 1 minus 1 over z plus 1 over z squared equals 0 divided by z squared, in other words, 0. It's not at all obvious how I'm going to factor this polynomial to solve, but there is a way to do it. The trick is to do a substitution. So pick some letter, I don't know, t maybe, and let that be equal to z plus 1 over z. How does that help? Well, this negative z and this negative 1 over z will just change into negative t, and this z squared and this 1 over z squared almost turns into t squared. Because look, if you square this thing, you get z squared plus z times 1 over z, in other words 1, plus 1 over z times z, another 1, plus 1 over z squared. So I can take this polynomial right here and kind of rewrite it cleverly. I can make it z squared plus 2 plus 1 over z squared minus, maybe in parentheses, z plus 1 over z minus 1. I go back and collect all the terms and make sure that makes sense. Here's my z squared. This 2 and this negative 1 is this 1. My negative z and my negative 1 over z go here, and my 1 over z squared goes here. This expression must be equal to 0, but if I do this substitution up here, this is exactly t squared, this is exactly t, so I get that t squared minus t minus 1 equals 0. I've gone from a 4th degree polynomial, which is difficult to solve, to a 2nd degree polynomial, which is pretty easy to solve. I don't know, quadratic formula, complete the square, whatever you like. Maybe I'll rewrite this as t minus 1/2 squared. That gets me my t squared and minus 1t. Unfortunately, it also gets me a plus 1/4. But if I write minus 5/4 here, the plus 1/4 from here and the minus 5/4 from here nets out to this -1. So this line's equivalent to this line. If I add 5/4 to both sides, I get here. Take the square root of both sides, and then add 1/2 to both sides. I get t is equal to 1/2 plus or minus the square root of 5/4. In other words, 1 plus or minus root 5 over 2. Remember, t is equal to z plus 1 over z. Z is equal to this number. 1 over z would be equal to this number, because when I multiply z and 1 over z, I get 1. And to multiply this complex number and this complex number, I add their angles, which would take me to 1. And if I add these two numbers up, their imaginary part goes away. So all I do is sum their real parts. I end up with some number over here. I don't know exactly what it's equal to, but it's clearly a positive number. Because t is a positive number, I'm not interested in the solution where I have 1 minus the square root of 5 over 2. The value of t that I'm interested in is 1 plus root 5 over 2. Okay, cool, but we don't want to know what t is equal to. We want to know what z is equal to. Well, we can immediately figure out the real part of z, because the real part of z and the real part of 1 over z sum together to create t, and the real part of z and the real part of 1 over z are the same. Therefore, the real part of z must be half of t. What I'm saying is this a value right here is just half of this number, 1 plus root 5 over 4. But this a value right here is just the x-coordinate of this point, which is defined to be equal to the cosine of this angle here, 36 degrees or pi over 5. Therefore, the cosine of pi over 5 must be equal to 1 plus root 5 over 4. Now that we know the cosine of pi over 5, if we could figure out the cosine of 3 pi over 5, I'd be able to prove that the sum of those two is just 1/2. In other words, the sum of the 4 primitive 10th roots of unity are exactly 1. Well, lots of ways we can do that. If you happen to know the triple angle formula, the minute you know cosine of pi over 5, you kind of know cosine of 3 pi over 5 for free. But I think there's a more clever algebraic way to do it. Remember up here, we got two different solutions for t, 1 plus root 5 over 2 and 1 minus root 5 over 2. Well, going back to this z here, we know that z to the 5th power equals -1. But if we instead focus on this point over here, maybe I'll call it w, and raise this to the 5th power, because this is 3 pi over 5, and 3 pi over 5 times 5 is 15 pi over 5. In other words, 3 pi, which is coterminal with 1 pi, which takes me over here to -1, w to the 5th power is also equal to -1. What I'm saying is another solution to this equation right here, this equation has 4 solutions, corresponds with this point. In fact, the 4 solutions to this equation correspond with my 4 primitive 10th roots of unity. Because if I take any of these points and raise them up to the 5th power, I end up over here at -1. So a minute ago when I was solving this equation, my goal was to figure out this value, which told me to discard 1 minus root 5 over 2. But maybe I should consider that solution where t is equal to 1 minus root 5 over 2. Because if I had set this problem up the exact same, except wrote a w everywhere I saw a z, then my substitution would have told me to let t be equal to w plus 1 over w. And since this value is w, this value is 1 over w, because if I multiply these two guys together, I end up with 1. And when I add these two values together, their imaginary part goes away. I end up with twice their real part, something over here. This would be my other value of t. Maybe I'll call it t naught, and let t naught be equal to w plus 1 over w. If t naught is 1 minus root 5 over 2, then what I'm calling c, the real part of this complex number, is half of that, 1 minus root 5 over 4. Therefore, the cosine of 3 pi over 5 is just equal to 1 minus root 5 over 4. And now I see when I add this number to this number, the root 5 parts cancel out. I get a fourth plus a fourth, in other words, a half. The cosine of pi over 5 plus the cosine of 3 pi over 5 is just equal to 1/2. That's kind of cool.